In the deepest silences of the cosmos, light travels. It is an ancient messenger bearing tales from a time before our species learned to harness fire, before our world had a name. This luminescence journeys across gulfs of emptiness so vast they defy our comprehension, carrying within its subtle fluctuations a coded history of its origin. For millennia, we could only guess at the stories it told. We looked up at the pinpricks of distant suns and saw only beauty, a canvas of divine mystery. But now we have built an eye, an extraordinary sentinel perched 1,000,000 miles from Earth, unblinking, untroubled by the blurring shroud of our atmosphere. It is a marvel of gold and gossamer, an instrument of such exquisite sensitivity that it can capture the faintest, most ancient whispers from the dawn of time. This great infrared observatory, the James Webb Space Telescope, was not designed merely to see farther, but to perceive differently. It senses the universe in a spectrum of light, invisible to us, a realm of cosmic heat and hidden chemistry. And in the cold, dark folds of a neighboring galaxy, this incredible instrument has intercepted a message. It is not a signal of intelligence, not a broadcast from a civilization. It is something far more elemental, perhaps even more profound. A chemical whisper, a familiar scent from an impossible distance. It is the signature of vinegar. To understand the magnitude of this discovery, we must first appreciate the messenger itself. The story of the Webb telescope is a human epic of ambition, ingenuity, and persistence. It began as a dream on paper, a successor to the legendary Hubble, designed to answer questions Hubble itself had raised. Questions about the very first stars, the genesis of galaxies, and the cradles where planets are born. To answer these, astronomers needed to see the primordial universe. But the universe is expanding, and as it stretches the light traveling through it. Light from the first stars, which began its journey as brilliant ultraviolet or visible light, has been stretched over 13 billion years into the long, slow wavelengths of the infrared. Our eyes cannot see it. Our atmosphere absorbs it. A new kind of telescope was required, one that operated in the cold, stable environment of deep space, far from the thermal glare of Earth. Engineers conceived of a primary mirror of unprecedented size, over 6 meters, across too large for any existing rocket fairing. Their solution was an act of mechanical origami, 18 hexagonal segments of beryllium coated in an exquisitely thin layer of pure gold designed to unfold in the void. This golden eye needed to be kept unimaginably cold, less than 50 degrees above absolute zero. Any heat from the instrument itself would blind it, a form of cosmic tinnitus, drowning out the faint signals from the abyss. The solution was a sunshield the size of a tennis court, composed of 5 layers of a material called capton, each layer thinner than a human hair. This colossal gossamer shield would stand between the telescope and the sun, earth, and moon, creating a permanent shadow of profound cold. Its launch and deployment was a sequence of over 300 single points of failure, a ballet of engineering precision performed 1,000,000 miles away with no chance for repair. Yet it succeeded. Humanity's golden eye opened, and the universe as we knew it was forever changed. The telescope's gaze was directed towards a familiar neighbor, a celestial companion to our own Milky Way. Not a galaxy in the far-flung cosmos, but one of our own celestial satellites, a member of our local group, the Large Magellanic Cloud, a dwarf galaxy that appears as a faint ethereal smudge in the southern sky, a river of 100 billion suns. It is a chaotic and vibrant place, a cosmic metropolis, undergoing furious bursts of star formation, far more active than our own more settled galactic home. Within this stellar island, Webb focused on a specific region, a place known to astronomers as a protostellar core. Imagine not a star, but the seed of a star. A vast freezing cloud of molecular hydrogen and interstellar dust hundreds of times larger than our own solar system. It is a place of profound darkness and cold, a stellar womb where gravity is slowly, patiently gathering material. In the heart of this frigid cloud, a nascent star is beginning to ignite, warming its immediate surroundings. It is in these dark, dense, and frigid nurseries that the story of planets and perhaps life truly begins. These are the places where the raw materials of creation are stored. To decipher the contents of this distant cloud, astronomers employ one of science's most powerful tools, spectroscopy. Think of it like this. If you shine a white light through a prism, it splits into the familiar rainbow of colors, a spectrum. But if that light first passes through a gas, you will notice something strange in the rainbow. Tiny dark lines will appear, gaps where specific colors are missing. Each element, each molecule, absorbs light at its own unique set of frequencies, its own characteristic wavelengths. These missing lines form a chemical barcode. By reading this barcode, an astronomer can know with certainty what the light has passed through, even from billions of light years away. The Webb telescope performs a similar magic, but with infrared light. It gathers the faint thermal glow from the heart of the protostellar cloud and passes it through its own sophisticated prisms. The result is not a rainbow, but a complex graph of intensity versus wavelength, a jagged line of peaks and valleys. Each dip, each absorption feature in that line is a clue. It is the signature of a specific molecule vibrating and rotating in a particular way as it absorbs the energy from the nascent star. Scientists sifted through this complex data, a stream of information from a place 1600000 light-years away. They found the expected signatures of simple ices, water, carbon monoxide, carbon dioxide, the mundane, ubiquitous components of any cosmic cloud. But then, buried in the noise, they found a more complex pattern, a series of faint absorptions that did not belong to any simple molecule. Painstakingly, they matched this pattern against laboratory data, comparing the cosmic signal to the known chemical fingerprints of countless organic compounds. And there it was, unmistakable, the barcode for acetic acid, CH3COOH, the primary constituent of household vinegar. And critically, it was present not as a gas but as an ice. This means the molecules were not freely floating, but were frozen solid onto the surfaces of tiny interstellar dust grains. They were preserved, protected within the cold, dark heart of the cloud like ingredients stored in a cosmic freezer. The significance of this finding is not in its taste or smell, but in its profound connection to the chemistry of life. Acetic acid is a complex organic molecule, a term which in chemistry simply means a molecule containing carbon atoms, often bonded with hydrogen, oxygen, and other elements. Life on Earth is exclusively carbon-based. Carbon's unique ability to form 4 stable bonds allows it to create long, complex, and diverse chains and rings, the very backbone of biology. But where did the first complex organic molecules on the primordial Earth come from? This question has haunted scientists for a century. In the 1950 seconds, the famed Miller-Urey experiment offered a clue. They simulated the conditions of the early Earth's atmosphere in a flask with water, methane, and ammonia, and zapped it with electric sparks to mimic lightning. Within weeks, the clear water had turned into a murky reddish-brown soup, and in it they found amino acids, the building blocks of proteins. The experiment demonstrated that the leap from simple inorganic chemistry to the complex organic molecules of life might not be so difficult after all. Acetic acid is a critical player in this prebiotic story. It is a simple carboxylic acid containing a specific chemical group that is also a fundamental component of every single amino acid. It is in essence a major prefabricated component for building proteins. Combine acetic acid with ammonia under the right conditions, and you can form glycine, the simplest amino acid. Furthermore, acetic acid is central to metabolism in nearly all known life on Earth. The process by which our own cells convert sugar into energy, the Krebs cycle, is fundamentally intertwined with acetate, the form acetic acid takes in water. Finding this specific molecule is like finding a key component of a factory, not just the raw bricks and mortar. It's not merely carbon, it is carbon that has already been assembled into a particularly useful and biologically significant structure. For decades we have known these ingredients existed beyond Earth. We have found amino acids inside meteorites that have fallen to our planet, celestial messengers carrying organic cargo from the asteroid belt. Missions to comets like the Rosetta probe have detected a rich cocktail of organic compounds, including glycine frozen in their icy nuclei. These discoveries confirmed that the building blocks of life could be synthesized in the harsh environment of our own solar system and delivered to the young Earth by cosmic impacts. This theory, known as panspermia, suggests that life on our planet may have gotten a chemical head start from extraterrestrial sources. Later, radio telescopes began to detect the signatures of simple organic molecules floating in the interstellar clouds within our own Milky Way. This expanded the canvas, suggesting that the ingredients were not just in our solar system, but were common throughout our galaxy. But the Webb's discovery of acetic acid ice in the Large Magellanic Cloud is a fundamental paradigm shift. This is not our solar system. This is not even our galaxy. This is a different stellar metropolis with a different history, a different chemical composition, and a different rate of star birth. And yet the same familiar chemistry is taking place. The same crucial life-enabling molecule is being synthesized and frozen onto dust grains in a stellar nursery 1600000 light-years from here. Imagine you are an explorer searching for a rare and beautiful flower. You first find it growing in your own garden, a source of local pride. Then you discover it also grows wild in the forests of your country. This is exciting, suggesting it is more common than you thought. But then an explorer returns from a completely new continent, a land separated by a vast ocean with different soils, a different climate, and a different evolutionary history, and in their hands they hold the very same flower. At that moment you realize the flower is not special to your home. It is a universal phenomenon. Its seeds are everywhere. The conditions for its growth are not a local fluke, but are baked into the fundamental rules of the world. This is the philosophical weight of finding acetic acid in another galaxy. It transforms the building blocks of life from a local phenomenon into a universal constant. The cosmic kitchen appears to be stocked with the same ingredients everywhere we look. The processes that create complex organic molecules are not a miracle unique to our little corner of the Milky Way. They are a robust, inevitable consequence of cosmic chemistry playing out in the cold, dark clouds of countless galaxies across the universe. This revelation forces us to confront one of the most profound and unsettling questions in all of science, the Fermi paradox. In the mid-20th century, amidst a casual lunch conversation, the brilliant physicist Enrico Fermi posed a simple, devastating question. Given the immense number of stars in our galaxy, the high probability of many of them having planets, and the vast age of the universe, there should have been ample time for intelligent life to evolve and spread throughout the cosmos. So he asked, where is everybody? The silence from the stars is deafening. This paradox, this great silence, has spawned dozens of potential explanations. Perhaps the leap from non-living chemistry to life is extraordinarily rare, a 1 in a trillion cosmic lottery ticket that Earth happened to win. This is the rare Earth hypothesis. But the discovery of interstellar acetic acid weakens this argument. If the necessary prebiotic molecules are ubiquitous, forming easily and universally, then the chemical foundation for life appears to be commonplace, not rare. So perhaps the filter is not at the start, but somewhere later. Perhaps life arises often, but the leap from simple microbial life to complex multicellular organisms is the great bottleneck. For billions of years, Earth was inhabited only by single-celled organisms. Maybe that is the cosmic norm, a universe teeming with microbes but almost entirely devoid of animals and plants. Or maybe the filter lies later still. Perhaps intelligence itself is the rare commodity. Or in a more chilling possibility, perhaps intelligence is not rare, but it is inherently self-destructive. Maybe any civilization that reaches a certain level of technological sophistication, the ability to harness nuclear power and travel in space, inevitably destroys itself through war, environmental collapse, or some other unforeseen catastrophe. In this view, the silence of the cosmos is not an absence of life, but the sound of a graveyard. The Webb's discovery does not solve the Fermi paradox. Instead, it makes the silence even louder, even more puzzling. It tells us that the universe is generously sprinkling the starter ingredients for life across galactic islands far and wide. The potential is everywhere. The flour, sugar, and water are in every kitchen. And yet, as far as we can tell, no one is baking. Or if they are doing so in perfect, impenetrable silence. This discovery is not an end, but a beginning. It is a single data point in a vast, unexplored cosmic ocean. The James Webb Space Telescope, with its extraordinary power, is now turning its attention from the nurseries of stars to the planets themselves. One of its primary missions is to analyze the atmospheres of exoplanets, worlds orbiting other stars. As an exoplanet passes in front of its host star, a tiny fraction of the starlight filters through its atmosphere. Just as with the interstellar cloud, the molecules in that atmosphere will absorb specific wavelengths of light, leaving a chemical barcode imprinted on the starlight. Webb is sensitive enough to read this impossibly faint barcode. Imagine the challenge: discerning the chemical makeup of a thin layer of gas surrounding a planet the size of Earth, orbiting a star hundreds of light-years away. It is like trying to determine if a moth flying around a searchlight 1,000 miles away has antennae by analyzing the searchlight's beam. Yet Webb can do it. Astronomers are no longer just looking for the building blocks of life in cosmic clouds. They are now actively searching for biosignatures, the chemical byproducts of life itself, in the skies of alien worlds. They will search for the tantalizing combination of gases like oxygen, methane, and water vapor. On Earth, oxygen is overwhelmingly produced by photosynthesis, and methane is largely produced by microbial life. Finding both in the same atmosphere would be a profound indicator, though not definitive proof, that some form of biological process is at work. The discovery of acetic acid ice in a protostellar cloud in another galaxy is a crucial piece of this puzzle. It tells us that the very molecules we might hope to find in an exoplanet's atmosphere are present in the material from which that planet will eventually form. The ingredients are placed in the mixing bowl right from the start. Future planets forming in that distant stellar nursery in the Large Magellanic Cloud will be born from dust and gas already seeded with the stuff of life. They will be preloaded with the very organic compounds that may have kick-started biology on our own primordial world. We stand at a unique moment in the history of our species. For all of our recorded past, the question, "Are we alone?" has been the domain of philosophers, priests, and poets. It was a question of faith, of speculation, of dreams. In a single generation, we have moved that question into the laboratory. It is now a query to be answered with data, with photons, with spectroscopic analysis. The journey began with ancient observers tracking the wandering planets, the wanderers in the sky, and wondering if they too were worlds. It continued with Galileo turning his telescope to Jupiter and seeing for the first time that other worlds had moons, shattering the idea of Earth as the center of all things. It progressed through the mapping of our galaxy, the realization that the faint smudges in the sky were other island universes, and the shocking discovery that these islands were rushing away from us in an ever-expanding cosmos. Now, with the Webb telescope, we have entered a new era of chemical exploration. We are cosmic archaeologists, sifting through the light of distant stars to uncover the chemical origins of existence. The detection of a simple, familiar organic molecule in a far-flung stellar cradle may seem like a small technical footnote in the grand cosmic story, but it represents a profound unification. It dissolves the boundary between the chemistry of life on Earth and the chemistry of the universe. The carbon in our bones, the oxygen we breathe, the iron in our blood, these were all forged in the hearts of dying stars billions of years ago. We have long known that we are made of stardust. Now we are learning that the stardust itself comes with assembly instructions. It is not just a random collection of elements, but a repository of complex, biologically relevant molecules ready and waiting for the right conditions to emerge. This discovery does not make our existence less special. On the contrary, it embeds our story into a far grander, universal narrative. It suggests that the potential for life is not a fluke, but a fundamental aspect of the cosmos, woven into the fabric of star-forming clouds from galaxy to galaxy. We look up at the night sky now, not as a void, but as a garden seeded with potential. The faint patch of light that is the Large Magellanic Cloud is no longer just a beautiful distant object. It is a place where we know for a fact that the same chemistry that ultimately led to us is taking place right now. Somewhere in that celestial mist, a future sun is being born from a cloud laced with the precursors to life. And perhaps billions of years from now, on a rocky planet orbiting that nascent star, something new and wonderful will stir, and it will look out into its night sky, see a faint, distant spiral galaxy, and wonder as we do if it is alone. The message from Webb is one of profound connection. A whisper of vinegar across the void, reminding us that we are not separate from the universe. We are its children, and the family resemblance is everywhere.